A single cargo hold on a wood chip vessel can swallow more than 10,000 cubic meters of material. But fill it with wood chips, and you've loaded less than 2,500 tons. That's the problem. Every year, nearly 6 million tons of American wood chips move across the Pacific, and the entire system exists to solve one engineering challenge. How do you keep low-density, irregular, combustible material flowing fast enough to fill a ship without blockages, heat buildup, or a dust event shutting the line down? Behind that answer is a chain of machines. A truck dumper that tilts a fully loaded trailer to 63 degrees. A stacker building a 100,000-ton pile one controlled pass at a time. And a grab crane cycling through a hold that needs to be loaded evenly or the vessel won't sail. Today, we're not following the wood chips. We're following the constraints. The 6 variables that decide whether a terminal ships on schedule or watches a vessel sit at the berth. Nearly 6 million tons of American wood chips move through export terminals every year. Each load travels aboard a vessel roughly 200 meters long, cargo holds wide enough to swallow a city block. But those holds can fill by volume long before they hit their weight limit. That gap is where the logistics problem starts. Every incoming truckload shifts the equation. Moisture content changes the bulk density. Particle size changes how the material flows. Dust fraction changes how safely it can be stored. Bark content and foreign debris change what the receiving equipment can handle without jamming. A single bridged hopper, a dust layer building heat in the stockpile, or one section of uneven material distribution. Any of these can interrupt the entire flow from truck gate to ship hold. A truck dumper rated to tilt at up to 63 degrees is only as effective as the conveyor running beneath it. This video will not just follow the machines. It will trace the technical limits that decide how long a 200-meter vessel sits at the dock waiting to be filled. The first problem begins before the chips even reach a conveyor. A cubic meter sits in front of you. Fill it with wood chips. Weigh it. You might record 220 kilograms. Fill the same cube with wood pellets. The scale reads 620 kilograms. Same space, nearly 3 times the weight. That difference is not about the wood itself. It is about the air between particles. Wood chips are irregular. They stack loosely. A cubic meter of freshly produced chips may contain 40% empty space or more. That space costs money to store, costs money to move, and costs money to ship across an ocean. Compare the same volume of sawdust. Finer particles pack tighter. Bulk density climbs to around 240 kilograms per cubic meter. Compress that sawdust into cylindrical pellets under heat and pressure. Density can reach 600 kilograms or higher. The pellets occupy less room per ton. Trucks carry more payload per trip. Stockpiles shrink. Ship holds fill with product instead of gaps. But pelletizing requires energy. A hammer mill grinds material to uniform size. A pellet press forces it through a heated die. Lignin softens and binds particles together. Cooling conveyors harden the cylinders. All of this demands electricity, equipment maintenance, and processing time. And some end users prefer raw chips. Pulp mills dissolve wood fiber in chemical baths. Pellets may need to be broken apart again before use. So the choice is not obvious. Ship low-density chips and accept more voyages, larger holds, and higher handling costs per ton, or compress material into pellets and pay for energy, machinery, and labor up front. A 200-meter ship with 5 cargo holds can carry roughly the same tonnage whether the load is chips or pellets. But chips fill the holds first. Weight capacity remains unused. The vessel sails with space occupied by product and air in nearly equal measure. That air cannot be invoiced. It cannot be sold to a paper mill, but it still crosses the Pacific, riding in a keel-balanced ship, monitored by crew, consuming bunker fuel for every nautical mile traveled. Low density turns logistics into geometry. The limiting factor is not the crane, it is not the truck, it is the cube. Two piles sit side by side on the terminal floor. One heads to a cargo vessel bound for Japan. The other gets burned as boiler fuel. They're both made of wood. They were both processed by machines within the last 24 hours. Which one would you load onto an export vessel? Look at the chip on the left. Clean cross-section, uniform size, roughly 25 millimeters across the longest face. No bark visible on the surface, no soil attached. Now the pile on the right, irregular edges, dark streaks of bark running through it. Particles ranging from dust fine to fist-sized chunks. Mixed species, mixed moisture, same raw material, completely different value. That second pile is hog fuel, and it is not a failed attempt at making wood chips. It is a separate product category, processed differently, sold at a lower price per ton, and fed into biomass boilers rather than pulp digesters. The problem is that footage of hog fuel and footage of export-grade chips can look nearly identical on a screen. Several engineers watching earlier footage pointed that out directly. They were right to flag it. So what actually separates one category from the other? 6 variables, every one of them measurable. Species composition. Softwood chips carry a different fiber length than hardwood. A pulp mill in Osaka has paid for a specific fiber profile. Mixed species changes that profile. Particle size distribution. Not just average size, the full spread from smallest to largest. A chip screen measures this by running material across graduated mesh openings. A chip with 90% of particles between 16 and 45 millimeters behaves completely differently in a digester than a pile where 30% of particles fall below 6 millimeters. Moisture content. Wet chips weigh more per cubic meter, but carry less usable fiber mass per ton. Buyers pay by weight. The difference between 45% moisture and 55% moisture changes the economics of every container shipped. Bark content. Bark increases ash. High ash chips reduce pulp yield and force additional processing at the receiving mill. Fines content. This is the variable most often underestimated. Fines are not simply smaller chips. A fine particle, anything below roughly 6 millimeters, changes the behavior of the entire bulk material. It fills the voids between larger chips. That reduces air circulation inside the stockpile and raises the risk of heat buildup during storage. Fines also compress under the weight of the pile above them, which reduces flow rate through hoppers and can create bridging, a condition where material locks across the hopper opening and stops flowing entirely. At the digester, fines cook faster than full-sized chips. Uneven cooking means uneven pulp. That reduces the fiber quality the mill paid for. The USDA Forest Service has published chip quality specifications distinguishing export-grade material from lower-value categories precisely because these differences have measurable downstream consequences, not because the chips look different on a conveyor belt. This is where the quality gate runs. Before any material reaches the loading terminal, it passes through a sequence of 4 checks. Chip screening. Material runs across a vibrating deck with multiple mesh sizes. Oversized pieces fall to a re-chipper. Fines drop through the bottom mesh and are redirected to the fuel pile. On-spec chips continue forward. Re-chipping. Oversized pieces, anything that did not pass through the primary screen, go back through a secondary chipper. Smaller knives, tighter clearance, same disc principle. Output goes back to the screen. Magnetic separation. Every load passes under a magnetic drum or belt before entering the export stream. Logging equipment leaves behind ferrous debris, wire, hardware, broken fasteners. A single piece of metal entering a pulp digester causes equipment damage and production downtime at the receiving mill. The magnet runs continuously. It does not sample. Moisture sampling. Random samples are pulled from each load. Some terminals use near-infrared sensors mounted over the conveyor for continuous monitoring. Others use manual sampling with oven drying. Either way, moisture data is recorded by load, by source, and by date. What happens when the wrong material enters the export stream? The costs compound in sequence. Material flagged at the loading terminal requires manual diversion. Each ton rerouted is a ton that was already screened, conveyed, and staged. That time is non-recoverable. Material that passes terminal inspection but fails at the receiving mill triggers a quality claim. The shipper may absorb the cost of regrading, handling, or rejection depending on contract terms. Beyond the single shipment, repeated quality failures reduce buyer confidence in the supply source. In a market where pulp mills contract supply years in advance, losing that confidence is not a one-shipment problem. A chip pile that passes all 6 quality variables does something the hog fuel pile cannot. It moves through the entire downstream system, the digesters, the washers, the bleaching stages, without creating friction at any point. That frictionless movement is the actual product being sold, not the wood, not the fiber, the predictability of the material. Even clean chips can stop moving once they enter a hopper. The receiving hopper after the truck dumper holds thousands of pounds of chips. A conveyor runs underneath, pulling material toward the stacker. But here's the problem. A full hopper doesn't guarantee flow. Sometimes the belt runs empty, while the bin above stays packed. Wood chips don't behave like water. Each piece has a different length, angle, moisture content, and surface texture. Those differences create friction between particles. Under the right conditions, that friction can lock the entire mass in place. One failure mode is called bridging. Chips interlock across the discharge opening, forming a self-supporting arch. The structure holds, even though there's empty space below. The conveyor keeps running, but no material reaches it. Weight from above presses the bridge tighter, not looser. Another is rat holing. Material flows through a narrow channel in the center, while the edges remain stationary. Old inventory sits against the walls. The feed becomes inconsistent. Operators can't tell how much material is actually left inside. Several factors make these problems worse. Long chips hook together more easily than short ones. High moisture increases cohesion. A high percentage of fines fills the gaps between larger pieces, reducing porosity. Rough hopper walls add drag. Shallow hopper angles don't provide enough slope for gravity to overcome friction. And when material is compressed by the weight above, particles wedge tighter. Increasing motor power doesn't solve this. If chips aren't reaching the belt, running it faster just moves air. Power consumption rises, but throughput doesn't. Engineers address flowability during terminal design. Hopper walls are angled steeply enough to prevent material from clinging. Liners reduce surface friction. Some systems use mechanical agitators or vibrators to break up bridges. Live bottom or screw feeders control discharge rate independently of the load above. The DOE Feedstock Conversion Interface Consortium has published flow testing protocols to predict behavior before construction begins. Breaking that bridge can restart the line, but moving dry material faster creates another limit. Once the chips leave the machinery, the risk does not disappear. It changes form. A single wood chip has limited surface area. 1 million particles ground to sub-millimeter size expose thousands of times more surface to oxygen. That ratio is what makes dust a different category of hazard entirely. OSHA identifies 5 conditions that must exist simultaneously for a dust explosion: fuel in particle form, oxygen, an ignition source, suspended dust, and an enclosed space. Remove any one of them, and the chain breaks. The problem is that a working sawdust processing line actively creates all 5 at once. The first explosion rarely destroys a facility. It dislodges the dust that is settled on beams, ledges, and conveyor housings. That cloud ignites in the pressure wave. The secondary event is what collapses structures. OSHA uses 420 microns as a reference threshold for combustible particle size. Particles above that threshold are less likely to stay suspended long enough to reach ignition concentration. But hammer mills and high-speed grinders routinely produce fines well below that number. And larger chips generate fines on impact even when the feed material starts above the threshold. Add into this section, the dust collector becomes the critical variable. It is the one component designed to remove suspended particles continuously. When throughput increases, the volume of airborne material increases proportionally. A collector sized for 80 tons per hour does not safely handle 120 tons per hour. Fines escape into ductwork, accumulate on surfaces, and wait. A magnetic separator pulls ferrous metal from the material stream before it reaches the grinder. When a piece of metal bypasses that separator, a broken bolt, a fragment of saw blade, a nail embedded in reclaimed timber, it enters a chamber spinning at high RPM. Metal on metal at that speed produces sparks. OSHA incident records document cases where a single contaminated load initiated ignition inside a grinder connected to a dust collection network. The real production limit is not grinder capacity or conveyor speed. It is the rate at which the facility can remove suspended particles, clean settled dust from surfaces, and verify that no ignition source has entered the feed stream. A plant that runs at 110% throughput for 6 hours and then shuts down for emergency cleaning has not outperformed a plant running at 85% continuously. Uptime, cleaning cycles, and maintenance intervals are part of the output calculation. The fastest grinder on the floor is only as productive as the housekeeping schedule that keeps it from becoming the ignition source. Every machine has stopped touching this pile. No conveyor running, no stacker arm moving, no grapple overhead. From the outside, 100,000 tons of wood chips looks exactly like what it is: a static mountain of raw material waiting for a ship. That surface reading is wrong. Inside a large wood chip pile, 3 processes run simultaneously without any equipment involved. Microbial activity breaks down organic material. Oxidation releases energy at the cellular level, and the sheer mass of the pile traps that energy with nowhere to go. The result? Heat builds from the inside out. A U.S. Forest Service study in Alaska documented this directly. Researchers instrumented a pile roughly 6 meters tall, with 25 sensor positions distributed from the outer edge toward the core. The material had been loaded under freezing conditions. Core temperature reached approximately 61 degrees Celsius. Not from external heat, not from equipment, from the pile itself. A separate study on pine chip piles recorded 2 distinct internal temperature bands: 146 degrees Fahrenheit at one depth, 137 degrees Fahrenheit at another. That's 63 degrees Celsius and 58 degrees, hotter than most industrial drying targets, generated passively inside a stockpile that looks completely stable from 50 meters away. Temperature gradients across a large pile can vary by 30 degrees Celsius or more between the outer layer and the interior. A chip pulled from the edge may read cool and dry. The same pile, 3 meters deeper, may be actively degrading. That gradient matters for 2 reasons. First, dry matter loss. Heat accelerates decomposition. Every degree above ambient means fiber converting to gas instead of staying in the pile as sellable material. Second, moisture redistribution. Heat drives moisture toward cooler zones. A pile that entered storage at uniform moisture content exits with uneven distribution, which affects pulping yield at the destination mill. Larger stockpiles compound both problems. A bigger pile buffers the terminal's schedule better. It absorbs the gap between continuous truck arrivals and a ship that loads once every several weeks. But a bigger pile also means a longer heat escape path from the core. The same mass that protects throughput also holds thermal energy longer, extends the degradation window, and makes representative sampling harder. At 100,000 tons, pulling 25 sensor positions the way the Alaska study did becomes operationally impractical. Most terminals rely on surface sampling and moisture spot checks, which, by definition, miss the thermal gradient entirely. Terminals use stockpiles to protect the schedule, but storage can only hide a weak link for so long. Every machine at this terminal has a rated capacity printed in its spec sheet. The truck dumper, designed to cycle every 4 minutes. The receiving hopper, built to absorb hundreds of tons per hour. The conveyor belt, rated to carry material at a fixed speed across the entire yard. The stacker, engineered to distribute chips across a 100,000-ton stockpile. Add those numbers together, and the terminal looks unstoppable. But rated capacity is not system capacity. Think of it this way. Water flows through a pipe only as fast as its narrowest section allows. Widen every other section by 50%. The flow stays identical until that one narrow point changes. A terminal with 5 machines operates on the same principle. Total throughput is not the sum of 5 individual ratings. It is determined entirely by whichever machine runs slowest or stops first. Here is a concrete illustration, and this is a hypothetical to show the math, not a specific terminal's data. Trucks deliver 500 tons per hour into the hopper. The conveyor carries 400 tons per hour toward the stockpile. Every 60 minutes, 100 tons accumulate in the hopper, with nowhere to go. After 4 hours, that gap reaches 400 tons. After 8 hours, the hopper is full. Trucks begin queuing outside the gate. The dumper sits idle, not broken, not slow, just waiting for downstream capacity to catch up. The hopper and the stockpile buy time. Both act as buffers, absorbing short-term mismatches between inflow and outflow. A 30-minute delay on the conveyor, the hopper handles it. A brief ship-loading pause, the stockpile absorbs it. But a buffer has a ceiling. Once inflow consistently exceeds outflow, the buffer fills, and the entire upstream chain stalls. The active bottleneck does not stay in one place. It shifts. Wet chips increase friction on conveyor belts. Throughput drops without any mechanical failure. A different wood species changes chip density. The same volume now weighs more, and the belt moves slower under load. One truck dumper goes offline for scheduled maintenance. Inflow to the hopper drops by half. A storm delays the ship. The stockpile fills while loading stops, and trucks have nowhere to deliver. A cleaning cycle on the belt system pulls 20 minutes of conveyor capacity out of every hour. The bottleneck is wherever the constraint lives at that moment, and when a machine stops, the effect does not stay local. The truck dumper halts. Trucks queue at the gate. Drivers wait. Scheduling breaks down. The conveyor stalls. The dumper empties the hopper, then has nothing to receive. The ship loading system pauses. The stockpile grows, but the vessel at berth keeps accumulating port fees by the hour. A ship waiting at berth costs money whether the crane is moving or not. That cost does not appear on any machine's spec sheet. The numbers worth tracking at a terminal are not the rated maximums. They are the real-time figures, actual tons per hour, not theoretical. Truck wait time at the gate, measured in minutes, not estimated. Hopper level, rising or falling. Conveyor idle time, percentage of each shift lost to stops. Downtime per machine, and what triggered it. Hours the vessel spent at berth before the hold was full. Hours lost to cleaning cycles, material jams, or weather holds. These are the numbers that determine whether a ship departs on schedule or sits at the dock for an extra 12 hours. The largest machine at this terminal is not necessarily the one that controls its output. The smallest gap in the chain does. That changes the final question. The goal is not to make every machine faster. An efficient terminal isn't one with the largest machines, the fastest conveyors, or the tallest stockpiles. It's one that balances inflow, outflow, quality, safety, dwell time, and uptime without letting a single variable spike. 6 constraints govern every operation. Ship holds limit total volume. Screening machines protect quality. Hoppers control flow rate. Dust collectors manage airborne particles. Temperature sensors track combustion risk. And the slowest machine in the chain defines throughput. Each failure has an economic consequence. A contaminated load gets downgraded. A truck waits an extra hour. A conveyor runs empty. A stockpile needs rework. A vessel stays at berth longer than scheduled. A processing line stops for cleaning. The value of this system doesn't come from how fast one chipper can reduce a tree. It comes from moving thousands of tons of low-density, moisture-variable, combustible material at the right quality, speed, temperature, position, and timing. That's not spectacle, that's control. And in bulk logistics, the fastest machine never sets the pace. The hardest variable to control does. Subscribe for more engineering breakdowns of the industrial systems behind everyday materials.